Okay, so in this video we will get to our second of our solver strategies for the non-homogeneous problem. So I think we mostly in this, let me go even further back. Okay, so our first method that we spent most of our time getting familiar with is this method of undetermined coefficients, which is useful if your ODE looks like this. Namely, of course, you have A, B, and C, which are just numbers in front of the y double prime, y prime, and y term. And the G of t over here on the right-hand side, of course, that's what makes it non-homogeneous, is that that's not 0. We discovered, I guess, that an easy, reasonably easy way to solve, to get one non-homogeneous solution is to make a guess for G of t. And if we make a guess, according to the chart that we're getting familiar with, run it through, we can figure out what our guess needs to be. And then the general solution is, of course, the homogeneous solutions, C1, Y1, C2, Y2, plus this one non-homogeneous solution that we acquire, this particular solution as we have been calling it, that we acquire from making a guess and from plugging it in and seeing what the guess is. But of course it's limited in the sense that this little chart or guide tells us that the right-hand side pretty much has to be one of these three, either an exponential, a sine and or cosine, or a polynomial. And while this method, and we did some examples, of course, of each of those, while it works, we might say, well, what else is there? Well, we discussed at least that you could maybe vary this a little bit by having some combinations of things in the chart. And while this is algebraically not super exciting to do, you could, in theory, if you absolutely had to, do that. And then I think what we did in the last video was to address the issue of what happens if the guess you're going to make is actually already represented in the solution by the homogeneous little y1 or little y2. And we discovered that a good way out of that that lets us still do the problem is to multiply our guess by t, or in some cases t squared, in order to produce a valid guess, or a fruitful guess, which still let us then find a particular solution. But of course, again, limitations. We still had to have a right-hand side that looked like something in our little guess chart. In other words, one of our three cases. So while it does work and gets us the answer to some slightly new problems, I'm still handcuffed by the idea that unless it is one of those things in the chart, and unless my left-hand side just has numbers, A, B, and C in front of the y double prime, y prime, and y term, I wouldn't know how to do it if I'm in any other situation. So perhaps, much like a lot of things in math, while we have some methods that work sometimes, it's nice to have a method that will work all of the time, so that at the very least it's sort of the fallback, and say, well, if I can't do undetermined coefficients, perhaps I can do the method that we'll talk about in this video, known as variation of parameters. So this is method 2. I don't know where I am with numbering, but we have method of undetermined coefficients and the variation of parameters method. I guess I could throw that in if you want. So these are going to be the two ways that we can find a particular non-homogeneous solution. And this one's always going to work. All right, so what does this method say, or what's this all about? So for an ODE, a second order ODE, non-homogeneous, that looks like this. So I'll give you the general appearance. Okay, so right? So if I have a general ODE, now what's different about this one than the one that we've been looking at for the last video or two is that you can have T stuff. Of course, right, P of T and Q of T just mean you might have some T's. So I don't know, T squared and sine of T, or who knows, right? Whatever you want. You can have those things. G of T is still the right-hand side, so I'm not messing with that. But I have to emphasize, and won't be able to emphasize enough, how important, I'll even do it in a different color here, how important it is that you have a 1 in front of the y double prime. So I will trick you, not on purpose, but maybe accidentally, that if you look at an ODE and there isn't a 1 in front of that y double prime, then absolutely everything we're about to say doesn't work. Now, I shouldn't say that it doesn't work. What I mean to say is that it will work, but you do have to make sure that you clear that out and get a 1 there, right? So it's very important. I'll jot that down, right? So we need to create a 1 here if it isn't already. Okay, of course, many of the problems already have a 1 there, so no big deal. But if you happen to have some stuff there, like a number, like 5, or even if you have some T stuff there, maybe you have a T in front of it, you got to divide through in order to clear that out before moving on. Now, of course, if you have something else in front, that might sort of, I don't want to say mess up, but it's at least going to alter what those 3 are. So if let's say I had a T in front of the y double prime, I would have to divide everybody by T. So of course that's going to change these other 3 characters too, which is totally fine. So don't worry about it. It's legal. It's obviously legal to divide through by whatever might be in front of that y double prime. So do so. All right. So it's very important that that be the case. I think we saw this in our back in February with our integrating factors approach. Right. We needed to have a 1 in front of the y prime, so that when we multiplied by u, it was u times y prime instead of something else. Right. Okay, anyway, all right. So clear that out is sort of step 1 in case it's not already cleared out. All right, so what's the idea? Okay, so for an ODE that looks like this, we'll say suppose we have the 2 homogeneous solutions, little y1 and little y2, which of course, if this is a problem like the ones we've been doing, right, like any of these, we know how to do that already, right? We know how to get little y1 and little y2. So this is not asking for a whole lot here, right? So if we have these 2 solutions, now it's either because we've computed them, like in the problems that we've been doing, or if we happen to have a nastier problem on the left, and in particular you'll see problems like this in the homework, where I don't think we actually know how to find the homogeneous solutions, but they might just be given to you, right? So if you see some problems that say, here's this awful ODE, and they tell you, oh, and little y1 is this, and little y2 is that, that's them giving you the 2 homogeneous solutions, and then you can still use this strategy to do the non-homogeneous portion, which is what I'm going to describe now. Okay, so either because you've computed them, or they were just given to you, or whatever, you have the 2 homogeneous solutions, little y1, little y2. Great. So the idea is but we of course know then that the general solution is going to be, C1y1, C2y2. But then we know that we need one particular non-homogeneous solution. So this is still the same setup as we've been dealing with all week. But where are we going to get that from? Well, especially if g of t, or whatever after you've modified it you have over there, if that's not one of the 3 types that's in our chart, I may be stuck, right? I may really be like, oh, well, geez, I'm not really sure how to do this then. So here's a strategy that's always going to work. So we have these, so we will guess, or I'll put it this way, if we guess that a particular, remember big Y is a non-homogeneous solution. So if we guess that we could get a non-homogeneous solution by doing our favorite trick, or we have a couple of favorite tricks, I guess, but one of our favorite tricks is to just use helpers in order to derive a solution that actually works. So here's what we're going to guess. So let's guess that if I did one helper, u1, times my little y1, right, that's my first homogeneous solution, and then maybe I have a second helper help me to modify little y2, my second homogeneous solution. Then if I make this guess, what am I really saying here is I'm essentially trying to build up a non-homogeneous solution out of the homogeneous pieces. Now, of course, these u1 and u2, those aren't going to be constants, because of course if those were constants, well, that would mean they were part of the homogeneous solution. But I think if I let u1 and u2 be functions, of course that means they have t's in them, well, that gives me a lot more to play with, right? That gives me a lot more freedom to decide what do they actually need to be in order to maybe force this to be a solution. So if we make this guess, right, so again, we know this and we know that. So our goal would be to say, if I'm going to make this guess, what of course am I going to do? I'm going to plug the guess into the ODE, and I'm going to hope that I'm able to solve for u1 and u2. In other words, those are my mystery helpers right now. So my hope is that through some work, I guess, we could come up with a way of identifying the correct or the appropriate u1 and u2 that will make this guess more than just a guess, it'll make it a solution. In which case I can do my usual summary at the end. All right? So, as usual, let's say, so if we get, we can run it through. And determine what u1 and u2, my two helper functions, must be to make our guess, yp, work. Okay, so we do stuff like this all the time, right? Make a guess, run it through, figure out what it needed to be, and then you have discovered the right solution, or a solution. Okay? Now, if I'm going to run this through, let me talk for 30 seconds before going on to a clean slide here. If I'm going to run this guess through that ODE, of course I'm going to need to plug it in for y. Then I'm going to need to take the derivative of it and plug it in for y prime. And then I'm going to need to take the second derivative of it and plug it in for y double prime, right? We do this for undetermined coefficients. Aha. Well, oh dear. So I would have to take this and drop that in for y, take the first derivative of that, drop it in for y prime, and take the second derivative and drop it in for y double prime. I mean, this is a hot mess of stuff right here. This is product rule and another product rule. So if I do one derivative, I have 4 pieces. So when I get to the second derivative, each of those splits into 2 pieces as well. I'd have 8 pieces. So I think we can all agree that nobody wants to see me do this, right? And this is the part where when we're in class, you're like, can I please just leave class now, because this is just god-awful, right? And well, the good news is you can, if I was going to torture you and do it, you could just fast forward the video to me being done. But don't do that, because I'm just not going to do it, right? Because it's just awful, right? But in theory, of course, I plug that in. Oh my gosh, I find crazy algebra tricks and rewrites and and a bunch of stuff simplifies, and we come up with something that's maybe not too bad. So we're just going to cut right to that chase and say, here's what you come up with. All right? So after running it through and doing an awful lot of simplifying, it turns out that we can compute the u1 and u2 we need by doing the following. All right, so of course when you run those through, you're going to get a whole bunch of stuff, and after simplifying, you end up basically with an ODE, a first order ODE for u1 and u1 and u2. So I'm going to just give you the punchline of then what those ODEs turn into when you solve them. So u1 of t is going to turn out to be something, and u2 of t is going to turn out to be something. All right, I have to give myself a little more space here. Okay, so I'm just going to jot this down. It is a little bit of a mouthful, I'm not going to lie, but when you do this in practice, it's not going to actually be that bad. So we're going to have to do so you end up getting an ODE for u1 and an ODE for u2. So of course, to solve those, it's not unreasonable to think that you might need to do an integral. And indeed you do, right? So as it turns out, u1 of t turns out to be the following integral. So here it is. So it's y2 of t times g of t over y2 of t y1 prime minus y2 prime y1 dt. All right, let me just jot them both down while we're here. And then the other one is basically you're mostly just swapping 1s and 2s here. Okay. All right, so u1 and u2, in order to determine who those mystery helpers need to be, well, it's these. So you just have to do two integrals, right, one for each, in order to compute the appropriate u1 and u2. Now, who's in this integral or these integrals that we're looking at? So first of all, remember, we already know. We know all the pieces. We know y1 and y2. Those are the two homogeneous solutions. You can certainly compute their derivatives. Right, because we're going to need those evidently, right? We need y1 prime and y2 prime and so on. And we know g of t, that's the right-hand side. So you know all of these things. I know it always looks a little bit awful when you see something, I don't know, gross like this or some formula. But all of the things, there's 6 things in each of these integrals, you know all 6. Or at the least you could very easily come up with those 6. All right? Now you do have to do an integral here. So, I mean, what I would be most scared of looking at this monstrosity is, what if this turns into a god-awful integral? And that's a valid concern. And in theory, I suppose it might. But I believe for the problems that we're going to look at, these will at least kind of turn out to be not too bad. Maybe an integration by parts, like one round, but nothing too crazy, all right? Okay, and now is where I'm just going to point out. So if I read this from top to bottom, remember, again, I have to be super, obsessive about this. If you don't have a 1 there, none of what I've just said works. So please, 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 please don't be the person that when you get a problem that had a 5 in front of that, instead of a 1, forgot to divide through by 5. Now, what effect is that going to have? Of course, if I did have a 5, let's pretend that 1 was a 5, then I'm going to probably end up with a 1/5 there, right? Because I'm going to divide through by 5. Well, of course, that's going to make, then I'm going to have 1/5 g. Okay? So it's whatever your ODE turned out to be, this g of t is whatever's on the right side after you've fixed it, right? So g of t is the right-hand side, the RHS, right-hand side, after you made sure a 1 is in front of of the y double prime term. Now, you may mess up the other coefficients, right? These guys would also get divided by 5, right? But that's okay because they don't actually appear in the formula, right? So, while, sure, you can rewrite it, but those, you don't have to worry about those. But g of t, the right-hand side, most definitely is part of this. So if you don't fix it, and that's where you're probably going to lead yourself to an impossible integral, which of course is wrong, like, you know what I mean? Like these are sort of somewhat rigged so that they work out kind of nice, but if you kind of have the setup wrong, you might find yourself chasing down some god-awful integrals, so maybe just double check, oh wait, did I get this set up right? Okay. So that's one thing to point out, is just caution on the g of t. The other thing that I'll at least just point out is if you look at the two denominators, they're the same, they're just, they're just negatives of each other. In other words, they're the same thing, you just swap them, right? Swap the terms. So, and these, this is known as the Wronskian. You don't have to know that, right? But if you see it in the book, I'll just at least point that out to you. The denominators right, that one and the one up top, after the arrow there, are the same just opposite signs. So when we do this, you'll see when we do our examples, when you go ahead and figure out how much that is, when you go to do the second one, don't redo the whole thing. Just write the same exact thing down there and throw a negative sign in front of it. Okay? All right. They're just opposite signs. And just FYI, in case you're dying to know, this is called, that one anyway, is called the Wronskian. Which, oh my god. Which if you've taken linear algebra, the Wronskian is the determinant. It's the determinant of the solution space, essentially. So anyway, none of that's important. But all right, so the good news is if we can do this and we can do these two integrals, you'll have u1 and u2, which means this guess that you have assembled over here is going to be more than just a guess. It's going to be an accurate working solution. And then we'll do our usual business at the end and say, oh, okay, I have one particular solution and my two homogeneous solutions, so I put it all together and I'm good to go. And this will always work, right? Nowhere did I say, oh, you got to make sure that you're blah, blah, blah. No, right? This will work no matter what you end up with. So this is sort of this is the quadratic formula, in the sense that it always works. Now, it's a little unpleasant, but it certainly always gets you to the answer. Okay, so let's at least try, I think I'll do 2 all the way out for you, and then leave you at least with a third one to just say a word or two about. So I will say, I think in the homework it tries to tell you which strategy to use. In real life, of course, unless I tell you on an exam you have to use one of these or the other, you could use whatever one you want. To be honest, I don't know, right? A lot of, I'm about to write down one that we could probably do either way, but it's probably about the same amount of work, to be honest. It's just sort of a question of, do you want to do a bunch of awful algebra, or do you want to do a bunch of awful calculus? So, I don't know. I guess personal choices, I guess. That's like a decision between lesser of two evils, I guess. But okay, so let's try this one. And this looks an awful lot like one that we do already know how to do with undetermined coefficients. So, if this was class, I would maybe start the clock and say, well, let's see how long it takes us with this, but probably about the same. All right, so to solve this with variation of parameters, I, of course, need to do the homogeneous solutions first. So let me do that very, very quickly. So this factors into -3 and -2. So we get 3 and 2. So little y1 is e to the 3t. And little y2 is e to the 2t. Okay, that took 12 seconds. So we got our two homogeneous solutions. And now in order to get our non-homogeneous solution, I'm going to first check, do I have a 1 in front of this? Yes, I do. Okay. So I'm good to go. I don't need to do any adjustment. So let's go. So let's try this. So variation of parameters says that you will get a non-homogeneous solution, u1, y1 plus u2, y2 is a non-homogeneous solution if, or for, the following computation of u1 and u2. So now I got to do these integrals. So u1 and u2, so I would just copy the formula from over here and put everybody in their place. Now, just a sort of pro tip here, since you're going to need to know, let's see, 6 things, or well, really 5 different things. G of t, I think I got that. I got y1 and y2, but I do need to know y1 prime and y2 prime. So just a little, I don't know, maybe it's more style than anything else, but I like to write down the derivatives of these guys because you know you're going to need them in a minute. It just sort of helps put you in the right headspace anyway, right? So if I do, these are both easy chain rules. So I have those. And some people like to compute the Wronskian, which again is the product of those two minus the product of those two. If you want to, you could write it down below here if you wanted to write it out first. But I think we're kind of, well, anyway, I'm just going to go though. All right. So I got my 4 pieces over here that I need. So I'm ready to try this integral. So the integral should be y2 times g of t, that's this one. So, and remember, if you have a number, like I have a 2 in front of this, I have to include that. I can't just omit that. So 2e to the t. Okay. All over. Now let's see, the denominator on this side starts here, so I get e to the 2t, 3 e to the 3t, minus, and then it's the other 2, 2 e to the 2t, times e to the 3t. Okay, so this looks bad, and this probably looks like we're heading towards some pretty awful integral. But try to sort of have some faith and that a lot of the stuff is actually going to cancel. So let's do a little bit of simplifying before we get too concerned here. So first of all, you can put the e's together. So up top there you have 2, and then you have e to the 2t and one more. That's e to the 3t. And on the bottom, let's see, those guys is I have 3, and that's e to the 5t, and then minus 2 e to the 5t. Oh, so on the bottom, you have 3e to the 5t minus 2e to the 5t, also known as e to the 5t. So I have 2 up top. Maybe I'll pull that out in front. So I have e to the 3t over e to the 5t. Well, that's not so bad. That's, again, just simplifying. That's e to the negative 2t. Well, that's an integral I can do in 5 seconds. Okay, so let's see, I end up with negative, because I would divide by negative 2, so that cancels with the 2, e to the negative 2t. That's it. Okay, so that wasn't too bad. So that's u1. All right, now to get u2, I'm going to do mostly the same integral, or, well, a lot of the same pieces. But now, of course, up top, I have y1. So I have e to the 3t times 2e to the t. Now, here's where you can save yourself a little bit of trouble. Whatever the old denominator was, it's the same, just with a negative. So how about I just cheat a little bit here and say that's negative e to the 5t. It is. I mean, if you do it out, you get the same thing, I promise. Okay, so what do we have here? Let's see. So I still have that 2, so I'll grab that and pull that out. What is that? E to the 4t up top, and e to the 5t down below. And I have a negative sign. Maybe I should put that with that 2, just so I don't lose track of it. So negative 2. So I have e to the 4t to the, oh, that's just e to the negative t, or 1 over e to the t. Oh, well, that's an easy integral. That's 2 e to the negative t. Okay, so I don't know how long that was, 5 minutes at most, of a little bit of calculus. And the good news is we now know that yp, remember, so our goal is to make our guess work. Well, our guess will work if we do that, if we use these u's. So now let's put it all together. So u1 is negative e to the negative 2t times y1. Oh, I got to go back over here. That's e to the 3t. And then u2 times y2. And most of the time, when you get to this point, you will have even more simplification that you can do. So this turns into, what's that, negative e to the t? And that's 2 more e to the t's, also known as, oh my goodness, just regular old e to the t all along. So who knew, right? But e to the t, maybe I should use a different. So e to the t is our one particular non-homogeneous solution. Okay, so as usual, here in our lower left corner, we will put our summary and say our general non-homogeneous solution is big Y. So C1, Y1, C2, Y2, plus our one non-homogeneous solution, this guy over here. Okay, now you could have gotten that with undetermined coefficients. In fact, I mean, if you had, this might have been one that was easier probably to do that way. But if you had, right, you would have guessed, what, a e to the t would have been your guess. So and apparently a turned out to be 1, right? Oh. So that might have been, I'll be honest, that probably would have been a little bit easier, but that's okay, right? We're got some good practice doing this new technique. All right, so I'll show you one more, and then we'll call it quits. Okay, so let me jot this second example down. So y double prime and y prime, and for y equals e to the negative 2t. Okay, so of course in order to do this, just like we did before, I need the homogeneous solutions. Well, when I'm thinking about this, I say, well, I'm not sure I know how to do this, but also thinking ahead to the variation of parameters, I do need to make sure I actually have a 1 there. So before I do anything else, let's maybe fix that and divide everybody by t squared. So if I divide everybody by t squared, negative, then I'd end up with that. Okay, now 2 good things happen. 1, we now know how to do the homogeneous solution. And 2, this is now in the right format to try variation of parameters. All right? So let's do the homogeneous very quickly here. So I get r squared and 4r and 4, which is r plus 2 squared, which means r is -1 and negative 2 and -2, which is our repeated root situation. And so little y1 is e to the negative 2t. But remember from earlier, our second solution, we put a t in front of it, right? So t, e to the negative 2t. Okay? All right, so we got our homogeneous done. More space. And now we got to do the non-homogeneous solution, which again, we could do this with, now I don't think we can, right? So if we were going to try this with undetermined coefficients, I'm not really sure what we would make as a guess for that. I mean, in theory you could do it, but it's not great. All right, so this is maybe the first example where we probably pretty much need variation of parameters because I'm not really sure how to do it any other way. All right, so let's try it. So I got a 1 in front of this, so that means I'm good to go. So this is my g of t. All right, and all right, so let's have it. So so yp is u1 y1 plus u2 y2. That's our guess. Well, it isn't really a guess anymore because we know it's going to work as long as u1 is this integral. Now, again, like I said in the last example, I think it's nice or kind of useful to write down the derivatives so that when I go over here, I don't have to go off and do a side problem. Now, unfortunately, in this one, in order to do the derivative of the second one, that's a product, which means I will need to use the product rule, which unfortunately is going to make this a little bit uglier. But I wanted to do a bad one so that you can see that it still turns out okay, but it's a little more unpleasant, I guess. So let's see. So I do have to do the product rule. So let's see. So that's negative 2t e to the negative 2t plus e to the negative 2t. All right, so it's not tragic, but I got to make sure I do the product rule. All right, so let's put everybody where they belong in the formula over here. So u1, in order to get u1, so if you need to look back, you can remind yourself u1, I like to remember it by saying u1 starts with y2, so you sort of start with the other one. Anyway, whatever. So y2 goes first, so that's t e to the negative 2t. And then a g of t, which is all of that stuff. And that's all going to be over. And I start with the same thing, y2. That goes with y1 prime. And then minus the other two. It doesn't really matter what order you put them in, so I'll put them in this order. Y1, and then negative 2 t e to the negative 2t plus e to the negative 2t. Okay. All right, so this is looking quite awful. But let's see if I can do a little bit of simplifying. So for sure, if I look at the numerator here, I have t and t to the negative 2. Well, that's t to the negative 1. And elsewhere, I have e to the negative 4t. All right. Now down below, it's my hope that I can make some simplifying before I actually try to have to do any real math here. So let's see. The first term here is negative 2t, and then I have e to the negative 4t. And now I'm going to distribute this so that I can see what I've got. So then what else do I have? I have plus 2t e to the negative 4t. Well, that's looking good. And then at the end here, I have minus e to the negative 4t. Okay. Oh, well, I love that. Those are the same, but one's negative, so that's 0. Oh, and that is the same as that. So my goodness, what am I left with? Negative, because I had a negative here. T to the negative 1? Well, that's no bad. That's no big deal. That's ln. So I get negative ln of t. So it looked a little dark for a minute there, but u1 turns out to just be negative ln of t. All right. So we're halfway there. I got to do u2 as well. I'm going to run out of space here, so just keep going. So I've got to do u2. So let's see. So just keep going. I'll start over here. So u2. So I'm going to look back for a sec. So u2, I start with y1, so that's e to the negative 2t. And then I have the the right-hand side, which is all of that stuff. So t to the negative 2, e to the negative 2t. And now here's where you can save yourself a little bit of trouble, which is that the denominator is exactly the same as the other one, just with a negative. Well, actually, geez, what did the denominator turn out to be? It just turned out to be negative 1. Right, this negative was really down there. It came from this one. So, So it's actually just 1. Oh, that's not true, because I canceled with stuff on the top. Okay, now I'm a terrible person. Okay, sorry. Okay, I got way ahead of myself here. Okay, I'm trying to be super slick here. So this is the denominator right here. So of course, yes, that is 0. So I'm probably not going to write that down again. But I do have that. All right, so sorry, before I get myself into trouble. The denominator was negative e to the negative 4t. So when I flip the sign, it's e to the negative 4t. Okay, sorry about that. Maybe I shouldn't be so slick. If you just do it out, you'll get this, right? So I shouldn't be so quick to try to make our lives easier. But I do like doing that because, of course, now we can all see, hopefully, that on the top you have e to the negative 4t. That's these two. And you have e to the negative 4t on the bottom. So actually, much like the last problem, this turns out to be a rather easy integral to do. Negative t to the negative 1. Okay, so that's our u2. So actually, I guess I could have fit it. I could have fit it at the bottom after all. But that's all right. So let's put our pieces together, and we'll come up with a final answer. So again, yp is now I have all 4 things I need: u1, y1, u2, y2. So let me write everybody down. So yp is u1, I think that was negative ln of t, y1 plus u2, that's the one we just did, times y2, which was t, e to the negative 2t. Right, so I think I got all my pieces in the right place, hopefully. Yes, good, okay. So as usual, there might be a little bit of simplifying or canceling here, so let me at least explore for a second here. This first piece, I don't think so, but I'll at least write it all together. Now in the second piece, let's see, I have t, and t to the, and that's 1 over t, so that's just 1. So I have minus e to the negative 2t. Okay, so that's my, I don't remember what notation I'm using, but that's my particular non-homogeneous solution. So let's pull our final answer together. So the general non-homogeneous solution then is big Y is, so C1 Y1 plus C2 Y2 plus our one non-homogeneous solution. Well, I guess they're both negative over there, so I guess I'll just go with that. But so plus negative ln of t times e to the negative 2t and e to the negative 2t. Okay, now here's where if we were together in class, I would say, now somebody tell me why what I wrote down is unnecessary or excessive. And here's where I would wait for you to think a little bit about that question. And some brave soul would raise their hand and hopefully say the following. So this is okay, but I would claim that there's a little bit of not quite goodness here. And what am I talking about? So let's read this from left to right. So from left to right, this says, hey, if you want to solve that ODE, that whole non-homogeneous thing that we started with, take any number of these, throw in any number of these, and then throw in those guys. Well, notice this is negative one of these. Is that right? Right, that's what it means to say that. But up front here, we just got through saying you can take any number of these. So this is a little silly because we're saying take any number of these and then take one of them away at the end. So if you want to be totally correct in a problem like this, when you get your non-homogeneous solution, or maybe I'll go up here, right, this guy. If any parts of it are absorbable, I don't know if that's a word, into the homogeneous portion, you can allow this to be swallowed up by that C1. Because, of course, remember, C1 is any number possible. So I don't need any number and then take one away. Just make a new C1. Now, I can't swallow this up. Oops, sorry. I can't make this get swallowed up because ln of t is not a constant. But 1 that's in front of this one, that's certainly a constant. Right, so really the right answer, the most correct answer, right, would be, here I'll write the word absorb. Oh boy. So this guy gets absorbed by that C1. So I would claim this is really the best final answer. So that's the one. Let's put a box around. Okay. All right. So that's pretty much it. I will leave you with a thought, just that in some of the homework problems, which is actually kind of good news, they, instead of them having, some of them, you're going to go through and you're going to compute the homogeneous solution like we did in these two examples. And then you're going to take that and do the variation of parameters, right? But in some of the problems, they're just going to give you the two homogeneous solutions. So for example, I think one of the actual homework problems is this. And they tell you that one homogeneous solution is 1 plus t, and the second homogeneous solution is e to the t. So they're going to give those to you. So that's nice of them. Right? That means, of course, you don't have to go track them down. Now, the reason why they gave them to you is because in this particular problem, you're not going to actually be able to compute them because the left-hand side has t's everywhere. Now, of course, I'll just, again, spoiler alert, tell you, don't do this problem like this, though, because, of course, I have to clear this t out. So here's the ODE that you really want to do. That's the one that you want to say, all right, I can do variation of parameters on that. Here's my little y1 and little y2, and I'm good to go. Here's g of t, and I'm good to go. All right? So good luck with these. Like I said, you should be able to hopefully finish these over the weekend. I think the homework is due on Monday, so hopefully you've had a chance this week to already go in and do, I think, the first half of the problems or maybe even more, were undetermined coefficients problems. But even if you haven't started those yet, they go pretty quickly too. So check them all out for Monday. If you have any questions, feel free to let me know. And good luck. If you have any other questions at all about anything, please feel free to reach out or pop in for some office hours. If you want to Zoom office hours at some other time, just shoot me an email with, can we Zoom at blah, 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 blah time. Much like you, of course, I'm home all day too. So we've got many opportunities to chat if you need me. So, all right, so good luck with this, and I'll be in touch. We are going to do a quiz next week, so I will email you some more details about how that's going to work.